Dear friends, welcome back to another episode in the series on geodynamics or dynamics of the earth. We have discussed in our previous two episodes the dynamic movements that take place on the earth's surface. We have seen how the various theories regarding the movement of the continents, the oceans and ultimately the lithospheric plates have been established with definite evidences. We have discussed two types of plate boundaries, the divergent boundaries and the convergent boundaries, of which there are three basic types. Before we go on to the discussion of the third type of plate boundary known as transform boundaries or conservative plate boundaries, let us discuss one important point of convergent plate boundaries. When the two plates are coming together, the leading edge of the overriding plate might scrape off some of the material from the downgoing oceanic plate, and when the oceanic plate is completely consumed and the overriding continental plate comes and collides with the overriding continental plate, these scraped off remains from the oceanic crust, that includes the pelagic bottom sediments together with part of the oceanic crust in the form of weathered and metamorphosed basalt, dikes, intrusive bodies and the underlying ultramafic rocks or peridotites. This sequence of rocks jumbled together, they are emplaced along the line of juncture or suture where the two continental plates collide. These oceanic crusts emplaced along suture zones on continents are known as ophiolites. An idea about the ancient oceanic floor can be obtained from these suits, because as we have already discussed, the oceanic crust disappears below another oceanic crust or a continent during the process of subduction, and no oceanic crust older than 200 million years, slightly younger than the Jurassic age, exists on the bottoms of the ocean floor of the present day. The ophiolites are a very good link to the past oceanic crust. Now let us transfer our interest to the third type of plate boundary, the transform boundary or transform faults. They are called transform faults because there is movement along the boundary parallel to the boundary in a horizontal direction. J.T. Wilson, who proposed the name transform boundaries or transform faults, demonstrated that oceanic ridges, divergent margins or convergent margins, they appear to be shifted along these transform faults. However, when divergent margins are shifted along the transform boundaries, the sense of apparent displacement that appears is quite different from the actual displacement of the plates on either side. For example, if there is a dextral displacement of the divergent boundary or oceanic ridge across a transform fault, the actual sense of displacement of the two plates on either side are actually sinistral. If you look at the direction of movement of the plates from a divergent margin and along the transform fault, this will be very clear. Since the displacement vector along a transform boundary is opposite to the apparent displacement of the divergent margin, instead of the usual strike slip or transcurrent fault, J.T. Wilson named these faults as transform faults. Transform faults are plate boundaries along which the plates on either side is moving parallel to it. However, the extension of the transform fault can also be observed beyond the divergent boundary segments or convergent boundary segments they connect. The active zone of the transform fault is only between the displaced divergent or convergent boundaries, but they extend beyond these boundaries as oceanic fracture zones, also called as fossil transform faults. The characteristic of the transform boundaries is that depending on the type of boundaries they connect, the length of the transform fault varies throughout its life period. The simplest form of transform boundaries that joins two segments of a divergent boundary remains constant in length throughout its life history, but when it joins a divergent plate boundary on one side and a convergent plate boundary on one side, or two convergent plate boundaries at two ends, depending on the polarity of subduction, polarity of convergence along the convergent boundary, it will depend if the length of the transform boundary will change in a positive direction or in a negative direction. It may shorten or it may get elongated. Though ideally transform faults are conservative boundaries where new lithosphere is neither created nor destroyed, there are some occurrences where the movement of the plates on two sides of a transform boundary, instead of being exactly parallel with it, are at a slight angle. If these movement at a slight angle to the transform boundary is away from the plate boundary, then there is opening up of the transform fault slightly, that results in creation of some new lithosphere on the ocean floor. Such transform faults are known as leaky transform faults. Transform faults are also characterized by the apparent displacement between the magnetic anomaly stripes on either side of a divergent plate boundary. This is when one segment of the divergent plate boundary on one side of a transform fault grows at the expense of the other. When these two segments are at a slight angle, there is an angle between the magnetic anomaly stripes developed against them, and one of the magnetic anomaly stripes, one set of magnetic anomaly stripes may overlap the other segment at an angle, thus giving the appearance of an apparent displacement. Hence, this phenomenon is called pseudo faults. Transform boundaries on the ocean floor are also characterized by shallow level earthquake focus, because the movement, the strike slip movement along the transform faults results in the release of energy in the form of seismic waves. Transform faults on the ocean floor have no component of up and down or vertical movement along them. The movement is in most cases entirely along the strike, and in certain cases at a slight angle, but in a horizontal direction. However, the transform faults in some cases are the sites of the steepest and highest scarps on the ocean floor. Let us briefly discuss how it happens. If the transform faults displaces a ridge boundary and the ridge boundary is a slow spreading one, then the portions or segments of the ridge that it brings together, one close to the ridge axis and another down its flank, it brings about the juxtaposition of two regions of the ocean floor which have a high difference in elevation. Due to this, though the displacement is almost horizontal, there appears that a near vertical scarp phase has developed on the ocean floor with a very high ridge crest juxtaposed against a much lower flank of another segment of the ridge. Oceanic transform faults are also characterized by the distribution of the oceanic lineaments, like the strikes of normal faults parallel to the divergent margins, the fractures, extensional fractures, the orientation of dikes that has come up through these fractures or normal faults. They become rotated toward from a perpendicular position to the transform fault to a gradual parallelism with the transform fault, because they are dragged due to the movement of the plates on either side. This gradual curvature, asymptotic curvature of the lineaments on the ocean floor are characteristic of transform faults. Though strictly speaking there is no generation of new lithosphere, it so happens that the width of the transform zones are not always very thin and sharply defined. Transform zones have variable topography, as the variable topography at mid-oceanic ridges or divergent plate boundaries depending on the spreading rate. The transform faults at different parts of the world separate divergent margins that have variable spreading rates. At slow spreading divergent margins, the transform faults that occur, they bring together segments of the oceanic crust which do not have much difference in their age. Thus, the transform zone is fairly well defined. In intermediate spreading rate ridges, the transform zone becomes slightly wide with dikes coming out through this zone parallel to the transform boundary. In fast spreading ridges, the transform fault brings about the juxtaposition of oceanic crust of highly different ages. Here the width of the transform zone is much wider with alternate ridges and valleys and with a number of intrusive bodies coming into the floor of the transform zone. Though the transform fault boundaries are found mostly on the ocean floors, at times they may continue onto the continents, and because of the continents preserving a thick sequence of very old rocks, the nature of the transform fault becomes different on the continents. The best example of a continental transform fault is the San Andreas fault in western North America in the California state. The continental continuations of transform faults has the more or less similar geometry, similar seismicity and similar fault movements, but the tectonism related to them are slightly different because on the ocean floor they affect only the thin newly formed crust, while on the continent they affect a thick continental crust which is many million years old. Now that we have discussed the various types of plate boundaries, the fragments of lithosphere that moves about on the asthenosphere, let us look at a cycle called the Wilson cycle of evolution of the Earth's surface relief. Since the middle of the 19th century till the 6th decade of the 20th century, the common belief of all scientists working with tectonics was that the evolution of the Earth's relief, the surface relief of the Earth, is related to the formation of a geosyncline and its subsequent formation into a mountain chain. This gradual development of a elongated depression on the surface of the earth, continuation of deposition and subsidence till it reaches a limiting depth, and then folding up of these sediments into an elongated mountain chain or orogen, was believed to be the cycle that all mountain chains followed. Hence, it was called the orogenic cycle. However, the advent of plate tectonics theory established clearly that it is not necessary at all to conceive of a geosyncline as precursor to a mountain chain. The movement of lithospheric plates can easily explain the development of mountain chains like the Himalayas or the Alps. Hence, the theory of geosynclines was completely discarded, but since it has been well established in the minds of scientists and students of science for nearly 100 years, it was believed by the modern scientists that if the present evolution of the earth's surface by plate tectonic theory can be expressed in the form of a cycle, then it will be better understood and better accepted. J. Tuzo Wilson, the same gentleman who proposed the transform faults, saw that the Atlantic Ocean, the present day Atlantic Ocean, which is gradually expanding, was preceded by another ocean which he named the Iapetus Ocean, when the two sides of it were formed into a single continent. So, he believed that the rifting of a continent is the beginning of a new plate tectonic cycle. According to him, first there is a continental rifting which is at the present day represented by the East African rift system. This continental rifting, as it continued, finally resulted in the opening up of the continent and exposure of the underlying basaltic crust which formed the beginning of a new ocean. The present day example is the Red Sea, which has opened up between the African plate and the Arabian plate, and the sea has transgressed into it. At the third stage, Wilson said that there was complete separation between the two segments of the initially single continent and a ocean with a mid-oceanic ridge and symmetrically disposed magnetic anomaly stripes form. This is what is happening in the present day Atlantic Ocean. In this situation, the margins of the continents on the both sides of the ocean that is thus created are passive continental margins. There is a boundary, a coastline with the continental crust on one side and the oceanic crust at the other side, part of the oceanic crust being covered by sediments, but there is no active tectonism in these regions. On the contrary, he said that some of the oceans like the Pacific Ocean are bounded by active continental margins where there is active tectonism along the boundary between the continent and the ocean, like the subduction zones, circum-Pacific belt or ring of fire surrounding the Pacific Ocean. So, in our next episode, we will be discussing transform faults and some other general features associated with plate boundaries. Thank you.